In this problem, we consider a variant of the Monty Hall problem where we have 3 doors, and the possible prizes behind the 3 doors could be the car, we could have a computer, or we could have a goat. And the contestant prefers the car to the computer and the computer to the goat. Now, the way Monty operates is Monty always opens the door that contains the prize that we prefer, the contestant prefers less. So, for example, let's say there's a car behind door 1. The contestant picks door 1 with the car, and now Monty will always open the door with the goat behind it because the contestant prefers the goat the least. If, on the other hand, we have the following permutation of prizes, so the first door contains the goat, then let's say the second door contains the computer and the third door contains the car, the contestant picks the first door. Now Monty will always open door 2 because the computer is less, the contestant likes the car more than they do the computer. So Monty will always open the door with the computer behind it. So we are also given the information that Monty opens the door revealing that it is a goat. And what we'd like to know is whether the contestant should switch to the third door or not. So let's label some events. We'll call CI the event that door I contains the car. So this is door I contains car. And D sub I will be the event that Monty opens door I. So D sub I will be the event that Monty opens door I. And O sub I will be the event that door I contains the computer. So door I contains computer. So the probability that we want to find is the probability that door 3 contains the car, given that Monty has opened door 2 and door 2 contains a goat. So if this probability if the probability is large, then we want to switch, because this is the probability that door 3 contains the car. The contestant has chosen door 1, so if this probability is larger than a half, then we should switch to get the most desired prize, which is the car. So we're going to use Bayes' rule here. So we get the prior probability that we have a car behind door 3 times the probability that Monty opens the second door and reveals a goat, given that there is a car behind door 3, over, now we're going to use the law of total probability. So we copy the numerator, D2 comma G2 given C3, plus the probability that door 3 doesn't contain the car, times the probability that Monty opens door 2 and reveals a goat behind it, given that door 3 does not contain a car. So let's look at the numerator here. The prior probability that door 3 contains the car is 1/3. The car is equally likely to be behind any of the 3 doors, so the probability that it is behind the third door is 1/3. Now, given that the car is behind door 3, what is the probability that Monty opens the second door and reveals the goat behind it? Well, the contestant has chosen door 1. So the third door contains a car. Monty always wants to open the door with the prize behind it that the contestant likes the least. So if the third door contains the car, which is the most preferred prize, Monty is definitely going to open door 2. And when Monty opens door 2, then the question becomes, what is the probability that door 2 contains a goat? Well, if we know that door 3 contains the car, then the goat is either behind door 1 or behind door 2, with both options equally likely. And so the probability that door 2 contains the goat is 1 over 2. Over, so we have 1 over 3 times 1 over 2 plus. Now what is the probability that the car is not behind door 3? That's 2/3. And now we want to know, given that door 3 does not contain a car, what's the probability that Monty will open door 2? And Monty will open door 2 and reveal the goat behind it. Well, let's rewrite that expression the following way. Let's say probability of there being a goat behind door 2, given that there is a car behind door 3, or there isn't a car behind door 3, multiplied by the probability that Monty opens that second door, given that there is a goat behind door 2, and there isn't a car behind door 3. So we just used the definition of conditional probability here, or rather we used the definition of the probability of a product, or the probability of intersection of two events, to rewrite this expression in terms of a product of these two probabilities. So now we have 1 over 3 times 1 over 2 in the numerator over 1 over 3 times 1 over 2 plus 2/3. Now, what is the probability that there is a goat behind door 2, given that door 3 doesn't contain a car? Well, let's look at our possibilities. So door 3 could contain the goat, and then we could have car here, computer here, or we could have goat, computer, car, or door 3 could contain the computer. So computer, we could have goat, car, computer, car, goat. And we're given that door 3 doesn't contain the car, so we can't have car be behind door 3. So there are 4 possible options, all 4 of them equally likely. And the one we're interested in is the one where behind door 2 we have a goat. Well, there is only one such option, namely this last one here. So the probability of that is 1 over 4. So times 1 over 4 here. And now, given that the third door does not contain a car, and the second door contains a goat, what's the probability that Monty opens door 2? Well, remember that Monty always wants to open the door that contains the prize we like the least. So if Monty knows that if the third door does not contain the car, and door 2 contains the goat, that means the car was behind door 1, door 2 contains the goat, and door 3 contains the computer. Now Monty has to choose between door 3 and door 2. Door 2 contains the goat, door 3 contains the computer. The prize between those two, the prize we like the least is the goat prize, the prize behind door 2. So Monty is definitely going to open door 2. So that probability is 1. And simplifying this expression, we get 1 over 2. Now moving over to part B. In part B, we're now told that Monty reveals our less preferred price with probability P. So the probability that Monty reveals less preferred price, is P. And Monty, in this part, we're told that Monty opens the door, revealing a computer. So this time, Monty is going to open the door. Let's suppose Monty opened door 2, and Monty reveals that there's a computer behind it. So again, should the contestant switch? How likely is it that the car is behind door 3? So what is the probability that door 3 contains a car, given that Monty has opened door 2, revealing a computer behind it? So again, we apply the Bayes rule and we apply law of total probability. So we get the probability that there's a car behind door 3, this prior probability, times the probability that Monty opens door 2 and reveals a computer behind it, given that door 3 contains the car. Now in the denominator we apply the law of total probability, so we just copy this numerator, probability of D2 comma O2 given C3, plus the probability that the car is not behind door 3, times the probability that Monty opens door 2, revealing a computer, given that the car is not behind door 3. So again, the prior probability of the car being behind door 3 is a third. And this expression here, we can rewrite that expression by using the definition of probability of the intersection of two sets. That's going to be the probability that there is a computer behind door 2 given the car behind door 3 times the probability that Monty opens door 2 given that there is a computer behind it and car behind door 3. Like so. And now in the denominator, again, the prior probability of there being a car behind door 3 is a third. And again, we're going to rewrite this, the first term in the denominator the same way we did in the numerator. So that's probability of O2 given C3 times the probability of D2 given O2 comma C3 plus, now the probability that the car isn't behind door 3, the prior probability, is 2/3. And for now we're going to rewrite this expression. So the probability that Monty opens door 2, revealing a computer behind it, given that the car isn't behind door 3. Okay, so in the numerator, what do we have? We have 1/3 times. Now, given that there's a car behind door 3, what's the probability of the computer being behind a door 2? Well, the computer is equally likely to be behind door 1 and door 2, so that probability is 1/2 times. Now, what is the probability that Monty opens door 2, given the computer is behind door 2 and the car is behind door 3? Well, the contestant then has selected the door behind which we have a goat, and Monty, with probability P, wants to open the door with the prize behind it that we like the least. So the prize behind door 2 is the goat. Out of the two choices, the prize behind door 2 is the computer. Out of the two choices, the computer and the car, the computer is the prize we like the least. So the probability that Monty opens the door that contains the computer is P. Over, so 1/3 times 1/2 times P plus 2/3 times. And now again, what is the probability that Monty opens door 2, revealing there is a computer behind it, given that the car isn't behind door 3? Well, just like we did before, we can rewrite this. We can rewrite this by using the definition of the probability of intersection of two sets. And we can say, well, what is the probability that there is a computer behind door 2 given that the car isn't behind door 3, multiplied by the probability that Monty opens door 2 given that there was a computer behind door 2 and the car wasn't behind door 3. So by the same logic as in part A, let's rewrite this part here, 1/3 times 1/2 P plus 2/3. So by the same logic as in part A, the probability that there's a goat behind the second door, given that the car isn't behind the third door, is 1/4. And now if we're told, now that we're given that the computer is behind door 2 and the car is not behind door 3, that means the car is behind door 1, the computer is behind door 2, and the goat is behind door 3. Now, what is the probability? What is the probability that Monty will open door 2? Well, notice that between door 2 contains the computer and door 3 contains the goat. So door 2, out of the computer and the goat, door 2 contains the prize we like more. And what is the probability of Monty opening the door that contains the prize we like more? Well, that is 1 minus p, in other words, q.